Hello, everybody. Today we are going to work on our Notes 2.3. So if you want to pull out your packet and you can fill out your notes template, or you can find the notes template on your Google Classroom. We're going to talk really mostly about properties of matter, and then we're also going to get into some temperature and some phase changes. So when we talk about atoms or compounds or anything like that, we usually talk about and describe these as properties, types of properties. So properties, remember, are just a characteristic or a trait. It describes something. So if I ask you what would be a property of yourself, you can say, I have brown hair. That brown hair is a property of yourself. Okay, there are two different types of properties. We have physical properties and we have chemical properties. Physical properties we can be determined or observed without changing the identity of the matter or that sample. So when I said my hair is brown, I was able to determine that property without destroying the substance. Whereas a chemical property is a property of a substance that changes into a new substance, or I destroy that substance when I'm determining that property. So if I wanted to see if your hair was flammable, what do I have to do? I have to light it on fire. And when I light something on fire, what happens? I destroy that sample. And because I destroyed that sample, that is a chemical property. So here are some examples of physical properties. I can determine the boiling point of something, color, if it's slippery or not, if it dissolves in water, the odor, softness, hardness, and the density. We talked about density last week. I can determine the mass of a sample without destroying it. I could also determine the volume of the sample without destroying it. So that's why density is a physical property. Whereas some chemical properties, it burns in air, it explodes, it reacts with water, it reacts with certain metals. So you'll notice the key words in that box is it's reacting with something, okay? When something reacts with something else, it is completely changing that substance. So those would be chemical properties. So just to remind you, chemical properties can only be observed during a chemical reaction, and it is completely destroyed. We can't get that back again, whereas a physical property, we are able to determine it, and it is not destroyed. So when we talk about physical properties, we also talk about ways to separate mixtures. Now remember, mixtures are two or more pure substances physically combined, which means we can easily separate them out. However, there are different ways that we can separate mixtures. So we're going to talk about a few of them. So this right here is actually a distillation apparatus. And what it's really doing is it is separating out certain things, okay? So the few things that we are familiar with in terms of what we can do in our lab is filtering. Filtering is when we separate it based on particle size. The easiest example that I have for filtering is think about your coffee pot. You usually throw a filter in that coffee pot so you do not get the grounds in your coffee. Okay, it is separating out the larger particles and letting the smaller ones drip through. Drying. This removes liquid from a solid by vaporization. So if I think about when you go to the beach or the ocean and you go sit in the ocean and then you lay on the beach. Once that water dries, you actually still leave behind the salt on your body. So your body is very salty, but that is drying. Or evaporation. Distillation is when you boil a liquid, and they have two different boiling points. So the one that's going to boil first actually evaporates, and you catch it, and you separate out two liquids based on the boiling points. And then you have magnetic attraction. This is like if you're trying to separate out maybe salt and sand and iron. Only one of those three is actually magnetic, the iron. So you are able to use a magnetic and draw out the iron from that mixture. So a little bit more specifics. Here's a setup of a distillation. You're boiling this liquid right here. Right here, you're going to boil this liquid, and it's going to evaporate, so it's going to go up. And then what happens, it kind of cools down, and it goes through this, what we refer to as a condensing tube. And what happens is that gas turns into a liquid, and then notice how it is also at an angle, so it drips down into here. So now you have one liquid over here and one liquid over here. And the reason why we could do that is because they have varying boiling points. Temperature is a physical property because I can determine the temperature of something without completely destroying the sample. Just like every day, if you take your temperature, you're not destroying your body when you take your temperature. A thermometer is a device that measures the temperature, okay? We're going to talk more about temperature in a little bit. So most thermometers, you're actually used to seeing degrees Fahrenheit, okay? However, in the sciences, really, the system that we use is Celsius, okay? So we're also going to work through how to convert from degrees Celsius to Fahrenheit and vice versa. There are actually 3 different scales that you can use. Actually, there's a lot more than 3 in temperature, but these are the 3 most common in the sciences. You have your Fahrenheit, you have your Celsius, and you have your Kelvin. The reason why we have these 3 different kinds of scales is they use something different to determine that scale. They use a standard. So if you look at your Fahrenheit, notice how water freezes at 32 degrees Fahrenheit. However, in Celsius, it's 0, and it boils at 100. So in your Celsius scale, they use really water to determine that scale. The unique thing about Kelvin is this is what they refer to as an absolute 0 scale because there is no negative in the Kelvin scale, whereas you can see a negative in the Fahrenheit and the degree Celsius scale. So when we convert from Celsius to Fahrenheit, we take 9/5 times my temperature in Celsius and then add 32. To convert from Fahrenheit to Celsius, we take 5/9 times the quantity of your Fahrenheit minus 32. And the easiest one is when you convert Celsius to Kelvin. That's when you can take your degree Celsius and you just add 273 to it. So on a cold day, the thermometer reads 41 degrees Fahrenheit. What is the Celsius equivalent? So the thing you need to remember is to make sure that you write out what you have. So you have degrees Fahrenheit, and you're trying to get 2 degrees Celsius. And then you write your formula. Remember, whenever we're solving problems, we want to use this 5-step process. So we do 5/9 times the quantity Fahrenheit minus 32. Then our third step is always plug the numbers in, give me an answer, and then also make sure you put your units. Because if you put the number 5, I have no idea what you're talking about. I want to know what are the units on that number 5. Let's take a look at another one. When the thermometer reads 50 degrees Celsius, what Fahrenheit temperature is this? So again, use your 5-step process. We're trying to figure out degrees Fahrenheit, so that's my missing variable. I have Celsius. We're now using the other equation, 9/5 times Celsius plus 32. Plug things in. My answer here is 122 Fahrenheit. So now let's talk about temperature. So when we talk about temperature, a lot of times you think about temperature as being how hot or cold something is. That may be true, but we want to be a little bit more specific. When we talk about temperature, temperature is the measure of average kinetic energy of these individual atoms. So remember, in temperature, or when we think about kinetic energy is moving energy, okay? So the faster something is moving, the higher the temperature it's going to be. The lower the temperature, the lower the motion. So this morning, it was very, very cold when I came into school, so those molecules in the air were moving very, very, very slow. But throughout the day, the sun warmed them up. They gave them more energy, and so those molecules kept getting faster and faster. So the greater the kinetic energy of the atoms, the greater the temperature. So remember I said that in the Kelvin scale, there was an absolute zero? That means that at absolute zero, if temperature is the measurement of average kinetic energy at zero, that means that those molecules are not moving, okay? Remember when we talked, though, a little bit earlier that atoms are always moving. They just may be moving very, very slow. So that's why we actually have that Kelvin scale. So this next slide, you are all very familiar with my 3 phases or 4 phases of matter. So I'm going to kind of just quickly go through it, but it is something that we do need to remember once we start getting into phase changes. My solids are very tightly compacted. They hold their shape and they do not flow. And my molecules are vibrating very, very, very slowly. My liquids, they hold their volume. What that means is if I have a cup of coffee and say it's 50 milliliters of coffee and I pour it onto the floor, does the volume change? No, the volume of that coffee does not change. It's just now spread out over the floor. So my volume of my liquid never changes. However, the shape does. The shape in my coffee cup is different than the shape of that coffee on the floor. Gases are very, very free. Those molecules are very chaotic. They're moving very, very fast. And these flow like liquids, but they do not hold the volume. They can expand and contract to whatever volume that they are in. And then, of course, we have our plasmas. We very rarely get into plasmas, but you do need to know that there are 4 phases. This is where a gas, where the electrons have broken loose from the atoms. So this is where you think about, your stars and some lightning bolts. So when we think about phase changes, we know a phase change is when we go from a solid to a liquid to a gas. Okay, the thing you need to know, and some things that you do not realize, okay, is when you change a state of matter, you require energy. And in that phase change, so if I had an ice cube sitting on the counter, it is going to melt. Melting is a phase change. It is going from a solid to a liquid. During that phase change, that temperature of that object does not change. It remains the same. And that is something that normally you're not used to seeing because you just think that that temperature is changing. But anytime you are going through a phase change, the temperature does not change. So let's go through a few kind of vocab items that we have here, okay? We already talked about energy of motion, okay? When we talk energy that is moving, we are talking about kinetic energy. Stored energy is potential energy. Okay. When we have stored energy, we have also potential energy. When my molecules are going through a phase change, the thing that is happening is my potential energy is changing. When you increase the temperature of a solid, liquid, or gas, you increase its potential kinetic energy. Because remember, kinetic energy is your temperature. So if I'm changing the temperature, I also have to be changing their kinetic energy. That means they're moving faster and faster and faster. When a substance changes states, so solid to a liquid, liquid to a gas, or gas to a liquid, liquid to a solid, this is where we are increasing its potential energy. We are increasing the space or decreasing the space in between those molecules. Because if we go back to that picture way back here and we look at the molecules, the difference between my solid, liquid, and gas is also the space in between those. So how does it get from a liquid to a gas? We need those molecules to spread further apart. And where does that change happen? That change happens during a phase change.